Close your eyes and imagine the deepest silence you've ever known. Now imagine something even quieter, a void so complete that even the concept of emptiness doesn't exist there. Yet from this impossible nothingness, a single quantum whisper somehow birthed stars, galaxies, and the very atoms that make up your dreaming mind. Tonight, we'll trace the delicate thread that connects that first mysterious moment to this very breath you're taking now, unraveling the universe's most beautiful secret. What existed in the moment before moments learned to exist? In a state so profound that even nothingness would be too much of something, the universe trembled on the edge of possibility, not as emptiness waiting to be filled, but as infinite potential compressed into a mathematical point where every star, every world, every conscious thought that would ever arise waited in perfect, shimmering silence for permission to begin. Before time began, there was no rhythm to mark the passage of moments that had not yet learned to pass. No light travelled because there were no distances to traverse, no space stretched toward infinity, because infinity itself remained an unborn concept. In this state before states, reality existed as pure mathematics, equations floating in a realm beyond physical existence, describing possibilities that had never been tested on any stage of actual being. Existence trembled as quantum foam stirred at scales smaller than imagination could reach. At the Planck scale, where distances measure 10 to the negative 35th meters and time intervals last 10 to the negative 43rd seconds, the smooth fabric of space-time becomes a bubbling sea of uncertainty. Here, the very concepts of here and there, now and then, dissolve into probability waves that dance between existence and non-existence with every quantum heartbeat. In this quantum wonderland, virtual particles flickered in and out of being like thoughts in a cosmic mind. These weren't particles in any sense we would recognize, but probability ghosts that borrowed energy from the universe's bank of possibility and returned it faster than cosmic accounting could detect the transaction. Energy and time were locked in their own strange tango, where borrowing infinite energy was perfectly legal as long as it was repaid in infinitely brief moments. Within this trembling haze, energy and matter were inseparable, not because they were identical, but because the distinction between them had not yet been established. They existed in perfect unity, like dancers who had not yet learned their separate steps, waiting for the cosmic choreographer to begin the ballet of expansion that would teach them their individual roles in the symphony of existence. The universe existed as a singularity, not a point in space, because space itself remained unborn, but a state where all matter and energy that would ever exist was compressed beyond our concepts of size and density. This was not compressed matter, but something far more fundamental. Condition where every physical law we know breaks down, where temperature and pressure become meaningless terms, and where causality itself held its breath. This singularity was balanced on the razor's edge between nothingness and being, yet it was not emptiness but pregnant stillness, infinite fullness compressed into impossibility. Every atom that would someday form in stellar cores, every planet that would orbit a distant sun, every thought that would bloom in consciousness was already encoded in the quantum information of this primordial state, waiting like seeds in cosmic soil that had not yet learned to exist. What made this moment extraordinary was not its potential for explosion, but its profound patience. This was not a bomb waiting to detonate, but a breath being held, the universe gathering itself like a cosmic lung preparing to exhale existence into being. The mathematical equations that governed this state contained within themselves the instructions for their own transformation, the quantum uncertainty that made the singularity both perfectly stable and utterly unstable simultaneously. The laws of physics themselves waited in suspended animation. Gravity, electromagnetism, and the nuclear forces existed in perfect unity as a single superforce, their individual personalities not yet expressed. In this unified state, there was perfect symmetry, perfect balance, perfect potential, awaiting the cosmic moment when symmetry would break and the four fundamental forces would separate like instruments in an orchestra, finding their distinct voices. Time had no meaning because nothing changed, yet change was the only possibility that mattered. Without sequence, without flow, without the progression from one state to another, time remained dormant like a river waiting for rain. The universe existed in an eternal now that contained every possible future without committing to any particular timeline, poised in the quantum superposition that would soon collapse into the singular choice of existence itself. How does infinity learn to expand when it's already everywhere at once? In the briefest whisper of cosmic time, faster than light could dream of traveling, quicker than thought itself could form, the universe transformed from mathematical possibility into physical reality, not through destruction but through the gentlest birth imaginable, as space itself awakened and time discovered how to flow forward into the endless dance of existence. In less than a heartbeat that had not yet learned to beat, space bloomed outward like a cosmic flower opening to dimensions that had never existed before. This wasn't expansion into some pre-existing void. The universe was creating the very concept of outward as it grew. Every point simultaneously became the center of expansion, as if reality were a sphere growing from everywhere at once, painting existence across a canvas that was weaving itself into being with each passing moment. The universe swelled from a mathematical point smaller than a grain of sand to vastness beyond comprehension, in a process so rapid it challenges every analogy we might attempt. During inflation, which lasted perhaps 10 to the negative 32nd seconds, the cosmos expanded by a factor of at least 10 to the 26th. If a single atom underwent the same expansion, it would grow larger than a basketball, yet the universe's growth was immeasurably more dramatic, stretching from subatomic to cosmic scales in less time than light takes to cross a proton. As space expanded, it carried time along like a river, creating its own banks as it flows. Time and space weren't separate entities, but woven together into the unified fabric that Einstein revealed as space-time. The universe began its cosmic clock for the first time, though there were no observers yet to witness these first precious moments when causality learned to march forward and effect began to follow cause in ordered sequence. Heat unimaginable began to cool as the same tremendous energy spread across ever-increasing volumes of space. The initial temperature was so extreme that our usual scales become meaningless. At 10 to the 32nd Kelvin, thermal energy was so intense that matter and antimatter existed as probability waves in a plasma of pure possibility. As the universe doubled in size, its temperature halved, cooling with breathtaking speed from incomprehensible heat to merely billions of degrees in the first second alone. During this cooling, one of the most profound transitions in cosmic history unfolded with elegant precision. The forces of nature, which had been unified in perfect harmony during the singularity, began to separate like instruments in an orchestra, finding their individual voices after playing in perfect unison. Gravity was first to distinguish itself, peeling away from the other forces and establishing its eternal reach across vast distances, becoming the architect of cosmic structure. As temperatures continued their relentless descent, the strong nuclear force separated from the electroweak force, claiming its future role as the power that would bind protons and neutrons in atomic hearts. This wasn't violent rupture, but symmetry breaking, like water suddenly deciding to freeze into crystals, choosing one particular arrangement from among countless possibilities that quantum mechanics had held in superposition. Finally, as the universe cooled below 1 trillion degrees, still incomprehensibly hot by any earthly standard, electromagnetism and the weak nuclear force found their separate identities. The 4 fundamental interactions that govern all physical processes were now established: gravity sculpting space and time, electromagnetism weaving light and matter together, the strong force preparing to forge elements, and the weak force ready to power stellar transformations. The blueprint of everything to come was being etched into the fabric of reality during these first extraordinary moments. Tiny quantum fluctuations, stretched across cosmic scales by inflation, carried the genetic code of all future structure. These variations were incredibly subtle, differences in density of only 1 part in 100,000, yet they determined where every galaxy cluster, every galaxy, and ultimately every star system would eventually form. Within this expanding cosmos, the seeds of complexity were already planted. The universe had established not just the stage for cosmic evolution, but the fundamental rules that would govern the next 14 billion years of development. Every star that would ever shine, every planet that would ever form, every conscious being that would ever contemplate existence owed their possibility to the precision and elegance of this initial unfolding, carried within an ever-expanding cosmos that had learned, in those first moments, how to transform potential into the endless architecture of reality. What if light could be a prisoner, trapped for hundreds of thousands of years in a cosmic jail made of its own brilliance? In the universe's most patient liberation story, photons that had been born in the first moments of creation waited in eternal captivity until matter itself learned how to set them free, marking the cosmos's transition from blindness to sight, from opacity to transparency, from chaos to the first gentle order that would make all future beauty possible. For nearly 400,000 years after the great unfolding, the universe lived in perfect paradox, filled with brilliant light yet completely dark, glowing with the fire of creation yet opaque as the densest fog. This wasn't the absence of illumination, but light itself held prisoner, trapped in an endless cosmic pinball game where every photon that tried to travel was immediately captured and scattered by the dense soup of free particles filling all of space. As the universe stretched and cooled from its fiery birth, particles began their restless dance in the primordial plasma that filled every corner of existence. This wasn't matter, as we know it, but a seething ocean of fundamental components, quarks bound by gluons, electrons racing at tremendous speeds, and photons ricocheting endlessly between them in temperatures still hotter than the cores of the most massive stars that would ever burn. In this particle symphony, quarks discovered their partnerships and embraced through the strong nuclear force, forming the first protons and neutrons like cosmic dancers finding their rhythm. These newly forged atomic nuclei swam through the blazing soup, but they could not yet capture electrons to become complete atoms. The universe remained far too energetic. Any electron that attempted to settle into orbit around a nucleus was immediately knocked free by the intense radiation flooding space. During these long millennia, light existed as a captive in its own cosmic kingdom. Photons would travel only microscopic distances before colliding with free electrons, scattering in new directions like pinballs in an infinite machine. The universe glowed with magnificent radiance, yet it was completely opaque, a cosmic furnace where light could never journey far enough to illuminate anything beyond the immediate storm of particle collisions surrounding each photon's birth. Expansion brought salvation through the mathematics of cooling. As cosmic temperatures dropped below 3,000 degrees Kelvin, still hot enough to melt copper but cool by the universe's standards, something extraordinary happened. Electrons finally moved slowly enough to be captured by atomic nuclei, forming the first complete atoms in cosmic history. Hydrogen and helium emerged from the particle chaos like islands of stability in an ocean of energy. With free electrons finally bound into atoms, the cosmic fog that had imprisoned light for eons suddenly cleared in an event astronomers call recombination, though it was really the first combination of nuclei and electrons in the universe's history. In what must have been the most spectacular transformation in cosmic time, the opaque universe became transparent almost instantaneously across its entire volume. This liberation created the most magnificent sunrise imaginable. For the first time, the cosmos glowed not from chaotic scattering, but from pure energy released into crystalline space. Light that had been captive for hundreds of thousands of years suddenly found infinite highways stretching in every direction, free to travel unimpeded across the growing expanse of cosmic architecture. It was a radiant dawn beyond any earthly comparison, a flood of brilliance sweeping across the void, marking the first true illumination of existence. The universe had opened its eyes and begun to see itself, transforming from a glowing prison into a transparent cathedral, where light could finally fulfill its destiny as the messenger between distant realms of space and time. This ancient liberation still whispers around us in the form of cosmic microwave background radiation, the cooled remnant of that first light stretched by billions of years of expansion into gentle radio waves that fill every corner of space, carrying the fossilized memory of the moment when the universe learned to shine. Can mathematics compose music without instruments? In the cosmic concert that followed light's great liberation, the universe began writing its most delicate symphony, not with melodies we could hear, but with the gentle mathematics of temperature and time, as chaotic energy slowly transformed into the ordered architecture that would one day cradle the birth of stars, the formation of worlds, and the emergence of minds capable of contemplating their own cosmic origins. Temperature plummeted with the precision of a cosmic metronome as expansion raced ahead, carrying the same tremendous energy across ever-growing volumes of space. The universe was learning the art of patience, trading the violent intensity of its birth for something far more subtle, the measured cooling that would allow complexity to flourish. Each doubling of cosmic size cut the temperature in half, creating a thermal symphony that played out across millions of years. The chaotic particle storm that had defined the early cosmos began its graceful transformation into cosmic serenity, where once protons, electrons, and photons had collided in endless frenzy, now hydrogen and helium atoms drifted through space like celestial snow, their electrons finally able to maintain stable orbits around nuclei. The universe had discovered rhythm, trading explosive chaos for the gentle cadence needed to build lasting structures. From this cooling emerged a cosmos unlike anything that had existed before, a sea of hydrogen and helium, thin beyond earthly comprehension yet immense beyond imagination. In every cubic meter of space, enough volume to contain a small automobile, only a handful of atoms wandered through the growing darkness. The universe had become emptier than the finest vacuum ever created in terrestrial laboratories, yet within this apparent void lay infinite potential. Hydrogen, forged in the nuclear fires of the first few minutes, claimed 3/4 of all ordinary matter, while helium made up most of the remainder. These were the only elements that Big Bang nucleosynthesis had managed to create during those primordial moments of cosmic chemistry. They would serve as the sole ingredients for constructing everything from the smallest grain of cosmic dust to the largest galaxy clusters that would eventually span billions of light years. Yet this cosmic ocean was not perfectly uniform. Like ancient poetry written in invisible ink across the manuscript of space, tiny variations in density remained scattered throughout the expanding universe. These quantum whispers, stretched to enormous scales during inflation, were remarkably subtle, variations of merely 1 part in 100,000, yet they carried the complete architectural blueprint for every structure that would ever grace the cosmic stage. Where matter had gathered even slightly more densely, gravity began its patient artistry with forces so gentle they were weaker than the attraction between soap bubbles. Individual atoms started their unhurried pilgrimage toward these barely perceptible concentrations, beginning a migration that would unfold over millions of years as matter gathered into the loose filaments destined to become the scaffolding for future galaxies. From this gentle cooling, order began to take root in ways both invisible and profound. The universe entered the era cosmologists call the Dark Ages, not a period of despair, but of quiet preparation, when no stars yet illuminated space and no galaxies had learned their spiral dance. During these cosmic centuries, the fundamental architecture of existence was being established through processes too subtle for any observer to witness. Matter continued its unhurried choreography toward equilibrium, guided by gravitational forces that operated with clockwork precision yet leaf-like gentleness. Hydrogen clouds began their slow gravitational collapse, heating gradually as they compressed, preparing for the critical moment when they would reach the temperatures needed to ignite nuclear fusion and birth the first stars. The cosmos was composing itself for the next movement in its eternal symphony, the age when light would return not as liberated radiation, but as stellar fire, painting the darkness with nuclear flame. What force could be weaker than a whisper yet powerful enough to move galaxies? In the vast darkness following light's first freedom, an invisible artist began the universe's most patient masterpiece, working not with tools or materials, but with the gentlest attraction in nature, sculpting cosmic architecture so slowly that its handiwork would take hundreds of millions of years to reveal the breathtaking beauty hidden within the quantum seeds of creation. Gravity stirred as the quiet sculptor of the cosmos, awakening to its destiny as the universe's most persistent architect. Unlike the dramatic forces that had shaped creation's violent birth, the explosive expansion, the searing temperatures, the chaotic particle collisions, gravity worked with infinite subtlety, exerting influences so gentle they were barely stronger than the attraction between morning dewdrops, yet so relentless they would reshape the entire cosmic landscape. Invisible and endlessly patient, gravity began to draw matter together across the cooling void with forces that operated by principles both simple and profound. Every atom attracted every other atom, creating a cosmic web of invisible threads stretching across space. Though each individual gravitational pull was weaker than the force needed to lift a feather, when multiplied across the vast scales of cosmic architecture, these whisper-soft attractions became the irresistible currents that would guide the universe's evolution. In the expanding sea of hydrogen and helium, gravity detected variations so subtle they would have escaped any conceivable measurement device. The tiny fluctuations left in the primordial haze, quantum ripples stretched to cosmic proportions during inflation, became the seeds of everything magnificent that would follow. These density variations were extraordinarily delicate, differences of only 1 part in 100,000, yet they contained the complete genetic code for cosmic structure. Where the ancient universe was even fractionally denser, gravity began its gentle harvest with the patience of geological time. Atom by atom, particle by particle, matter started its slow pilgrimage toward these cosmic gathering points, moving like invisible rivers flowing downhill through dimensions of space so gradually that their movement was imperceptible to any observer, yet so persistent that nothing could resist their eventual pull. Dark matter, mysterious and invisible, to all forces except gravity, served as the universe's primary building material in this architectural phase. Making up 5 times more mass than ordinary atoms, dark matter felt only gravity's gentle touch, unaffected by electromagnetic forces or nuclear interactions. It gathered first into vast halos and filaments, creating the scaffolding upon which ordinary matter would eventually collect like cosmic ivy, growing on an invisible framework. These dark matter structures formed the cosmic web, a 3-dimensional tapestry spanning billions of light years, where matter collected along filaments connecting vast nodes while leaving enormous voids nearly empty between them. This network became the foundation upon which all future galaxies would be built, an architecture so grand it defies easy comprehension, yet constructed entirely from forces too weak to disturb a grain of sand. The process unfolded with cosmic patience across millions of years. Dark matter halos grew denser and more massive, their gravitational embrace strengthening until they could begin attracting the hydrogen and helium gas floating through space. As ordinary matter fell toward these invisible anchors, it began to heat up from compression, setting the stage for the cosmic drama that would follow. In this unseen architecture, the stage for all future creation was being quietly prepared. Gravity, working with the persistence of eternity and the precision of quantum mechanics, was weaving the cosmic theatre where stars would eventually ignite, galaxies would learn to spiral, and planets would form in the gentle warmth of stellar light. The silent architects had begun their masterwork. The hand that would shape eternity was drawing its first invisible blueprints across the cosmic dark. When does darkness become its own creator of light? In the deepest cosmic night that had ever existed, hydrogen clouds began a journey inward that would end in nuclear fire, not through destruction, but through the universe's first act of true alchemy, where the simplest atoms would sacrifice themselves to forge the elements that make complexity possible, igniting stellar furnaces that would burn with the brightness of creation itself. For hundreds of millions of years, the universe had waited in patient darkness, its hydrogen and helium scattered like cosmic seeds across the growing architecture that gravity had so carefully prepared. Within the invisible scaffolding of dark matter, gas clouds began their slow gravitational dance, drawn together by forces that had been accumulating strength across cosmic time, gathering mass and momentum for the transformation that would change everything. Darkness gave way, not suddenly, but through the mathematics of inevitable collapse as gravity compressed vast clouds of hydrogen with the patience of eternity. These primordial gas clouds were unlike anything that would ever form again, pristine collections of the universe's original elements, unmarked by the heavy atoms that future generations of stars would create. They were cosmic virgins, about to give birth to the first stellar children. As the clouds contracted, density rose with elegant precision, following the ancient laws of thermodynamics that govern all cosmic transformations. Gravitational potential energy converted to heat, warming the collapsing gas from the frigid temperatures of space to the modest heat of planetary cores, then to the searing temperatures of stellar interiors. The universe was learning how to concentrate its diffuse energy into focused points of incredible intensity. Pressure rose within these cosmic crucibles as atoms were squeezed closer together than they had been since the first moments after creation. The hydrogen nuclei, simple protons, began to move faster and faster, their thermal dance becoming ever more violent as gravitational compression continued its relentless work. The stage was being set for the most important chemical reaction in cosmic history. In the furnace of collapse, when temperatures reached 10 million degrees, Kelvin and pressures exceeded anything imaginable on Earth, fusion finally ignited, like a cosmic match striking against the darkness. Protons began their intimate dance of nuclear binding, overcoming electromagnetic repulsion through quantum tunneling and the strong nuclear force, transforming hydrogen into helium while releasing tremendous amounts of energy in the form of light and heat. The first stars blazed into existence as immense and short-lived giants, far more massive than the sun that would eventually warm our world. These stellar titans contained dozens or even hundreds of times the mass of future stars, burning with such fierce intensity that they consumed their nuclear fuel in mere millions of years, a cosmic eye blink compared to the billions of years that smaller stars would eventually enjoy. Their light pierced the cosmic night with unprecedented brilliance, scattering illumination across vast distances for the first time since the universe had become transparent. This wasn't the gentle glow of liberated radiation from recombination, but the fierce nuclear fire of stellar cores, painting space with photons born from the marriage of matter and energy in gravitational furnaces. These stellar pioneers began the universe's great work of element creation, forging carbon, oxygen, and heavier elements in their nuclear hearts. When their brief lives ended in spectacular supernova explosions, they scattered these new elements across space, seeding the cosmos with the chemical complexity needed for planets, life, and consciousness. The true dawn of cosmic structure had begun, marking the end of the Dark Ages and the beginning of the universe's long journey toward the magnificent complexity that surrounds us today. How does death become the universe's greatest gift to life? In the cosmic paradox that would define all future evolution, the first stars discovered that their magnificent destruction was far more important than their brilliant existence, transforming nuclear fire into elemental seeds that would drift across space for billions of years, carrying within their atomic hearts the very building blocks needed to construct planets, oceans, and the chemistry of consciousness itself. These ancient titans burned with furious brilliance that dwarfed anything the universe would ever see again, their nuclear hearts consuming hydrogen at rates so prodigious they could power thousands of suns like ours. Yet for all their spectacular intensity, these stellar giants carried within themselves the seeds of their own inevitable destruction, racing through their nuclear fuel with the desperate hunger of cosmic meteors burning through atmospheres of time. Unlike the patient, long-lived stars that would follow, these primordial furnaces lived fast and died young, their massive cores creating temperatures and pressures so extreme that they became cosmic alchemists, forging elements that had never existed before. Deep within their stellar hearts, helium fused into carbon in the triple alpha process. Carbon combined with helium to create oxygen, and successive fusion reactions built silicon, sulfur, and ultimately iron, the element that would prove to be their beautiful doom. Iron represented the end of the stellar road, the nuclear cul-de-sac, where fusion could no longer release energy, but instead began to consume it. As iron accumulated in the stellar core like cosmic ash building up in a furnace, the delicate balance between gravitational collapse and nuclear fire that had sustained the star for millions of years suddenly shifted. Gravity, patient and relentless, finally claimed its ultimate victory over the nuclear forces that had held it at bay. The collapse happened faster than thought. In less than a second, cores more massive than our Sun compressed to the size of cities, creating densities so extreme that protons and electrons were crushed together into neutrons. The shockwave that rebounded from this compressed core raced outward at thousands of kilometers per second, tearing through the star's outer layers and exploding into space with the energy of billions of suns. These violent supernovae became the universe's first great recycling program, scattering the precious heavy elements that stellar fusion had so carefully crafted throughout their nuclear cores. Carbon, the foundation of complex chemistry, oxygen, the breath of future life, silicon for rocky worlds and iron for planetary cores, all were hurled into space in expanding shells of stellar debris that would travel for millions of years across the cosmic void. From their spectacular deaths came the ingredients for everything meaningful that would follow. Future worlds built from silicon and iron, oceans formed from oxygen and hydrogen, and the carbon-based chemistry that would eventually give rise to life itself. The calcium in future bones, the iron in blood, the oxygen in every breath, all were forged in the nuclear hearts of these ancient stellar giants and scattered by their explosive endings. This cosmic cycle of stellar death and elemental rebirth established one of the universe's most profound truths. Creation was written not in permanence, but in cycles of fire and ash, where destruction and creation became partners in the cosmic dance. Each generation of stars would build upon the elemental legacy of those that came before, enriching space with ever more complex chemistry until the universe finally possessed the full periodic table needed to construct planets capable of harboring life. The ancient Titans had given the ultimate sacrifice, transforming their nuclear fire into the elemental seeds of all future complexity, proving that sometimes the most beautiful gift the universe can offer is the transformed ashes of cosmic death. What happens when billions of stellar children decide to dance together? In the cosmic choreography that followed the first stellar deaths, gravity began composing its grandest symphony, gathering individual stars into vast communities of light that would spiral through space for billions of years, creating the magnificent galactic cities where stellar generations would be born, live and die in endless cycles of cosmic renewal. As the universe continued its patient expansion and the ashes of the first supernova enriched space with heavy elements, something remarkable began to emerge from the cosmic dark. Stars no longer burned in isolation, but started gathering into gravitational communities, drawn together by the same invisible force that had collapsed the first gas clouds into stellar nurseries, now working on scales thousands of times larger. Within the scaffolding of dark matter that had been quietly growing since the universe's youth, ordinary matter began its grand assembly into the first galactic structures. These early galaxies were chaotic and irregular compared to the elegant spirals we see today, cosmic cities in their founding years, where stellar neighborhoods formed haphazardly as gravity sorted through the complex dance of gas, dust, and newborn stars. Stars gathered in vast spirals and elliptical clouds, bound by gravity into glowing cities of light that stretched across hundreds of thousands of light years. Each galaxy became a cosmic ecosystem where gas clouds collapsed into stars, stars forged heavy elements in their nuclear hearts, and stellar deaths scattered those elements back into space to seed new generations of stellar formation. The universe had discovered how to recycle its stellar children. These galactic communities were far from uniform. Some galaxies grew through gentle accumulation of gas and dust, slowly building their stellar populations over billions of years. Others formed through dramatic collisions and mergers as smaller galaxies were gravitationally captured and absorbed into larger structures, their stars scattered into new orbital patterns like cosmic immigration on the grandest possible scale. The Milky Way itself was among these early galactic pioneers, beginning as a modest collection of gas clouds and first-generation stars that would eventually grow into the magnificent spiral that cradles our solar system. Over cosmic time, it accumulated smaller galaxies, survived near collisions with cosmic neighbors, and gradually developed the elegant spiral arms that sweep through space like frozen hurricanes of stellar formation. As galaxies matured, they developed supermassive black holes at their centers, gravitational anchors millions of times more massive than typical stars, which helped organize stellar orbits and occasionally fed on surrounding matter, blazing as quasars that could outshine entire galactic communities. These central engines became the gravitational hearts around which hundreds of billions of stars would orbit for eons. In their cosmic clustering, galaxies formed the great web of the universe, stretching across unfathomable distances in a three-dimensional tapestry of matter and light. Gravity wove these galactic cities along filaments spanning hundreds of millions of light years, creating the largest structures in the cosmos while leaving vast voids nearly empty between them. This galactic architecture established the cosmic stage upon which all future stellar drama would unfold. Within these island universes, successive generations of stars would create increasingly complex chemistry. Rocky planets would form in the gentle warmth of stellar light, and eventually, on at least one small world orbiting an ordinary yellow star, the carbon and oxygen forged in ancient stellar hearts would combine into the molecules that would give rise to life, consciousness, and the ability to contemplate the very cosmic journey that created the elements from which we are made. What if the universe were an artist painting with galaxies instead of pigments? In the cosmic masterpiece that emerged over billions of years, matter arranged itself into the most elegant architecture imaginable. A three-dimensional web spanning the entire observable universe, where luminous threads of galaxies stretch across the darkness like celestial highways, connecting islands of starlight in the vast ocean of cosmic space. As galaxies matured and multiplied across cosmic time, a grander pattern began to reveal itself, one so vast that no single observer could perceive its full magnificence. The universe was arranging its matter not randomly, but according to an ancient blueprint written in the quantum fluctuations of its birth, creating structure on scales that dwarf individual galaxies the way galaxies dwarf individual stars. Threads of galaxies stretched like luminous filaments across the universe, following the invisible highways carved by dark matter billions of years earlier. These cosmic superhighways weren't straight lines, but graceful curves that bent and twisted through three-dimensional space, creating a network so intricate that it resembles neural pathways in a cosmic brain or blood vessels in some vast celestial organism. Along these galactic filaments, matter flowed like cosmic rivers carrying gas, dust, and entire stellar communities toward gravitational destinations that had been predetermined by the universe's earliest moments. The journey was patient and persistent, streams of matter traveling for hundreds of millions of years along these cosmic conveyor belts, guided by gravitational currents, too gentle to feel yet too persistent to resist. At the intersections where multiple filaments converged, gravity's influence intensified dramatically, creating cosmic metropolitan areas where thousands of galaxies gathered into massive clusters. These galactic cities stretched across tens of millions of light years, containing more matter than 1 trillion suns, held together by gravitational forces that bend space and time itself into curved architectures of impossible beauty. Between the bright filaments lay something equally profound, vast cosmic voids, regions of space so empty they contain almost no galaxies at all. These cosmic deserts stretch across hundreds of millions of light years, creating the shadows that give definition to the web's luminous threads. In the cosmic tapestry, darkness proved as important as light, emptiness as crucial as matter. This cosmic web was not random, but represented the quiet geometry of gravity working across the largest possible scales. Every cluster, every filament, every void traced back to the tiniest quantum fluctuations that had rippled through the universe during its first moments. The cosmos had grown like a crystal, following patterns encoded in its primordial structure, expanding these ancient blueprints to scales spanning billions of light years. The web's architecture revealed the universe's most fundamental truth, that matter and energy organize themselves according to mathematical principles that transcend any individual component. Just as molecules follow chemical laws to create complex structures, and cells organize into tissues and organs, galaxies arrange themselves into cosmic organs, following gravitational laws that create beauty through pure physics. Within this grand structure, our own local group of galaxies occupies a modest position along one cosmic filament, part of a larger supercluster that stretches across hundreds of millions of light years. We exist as cosmic suburbanites in this vast metropolis of matter and light, connected by invisible threads to the largest structures in the universe. The cosmic web continues evolving even now, its filaments growing stronger as gravity pulls more matter along their lengths, while cosmic expansion slowly stretches the spaces between them. This eternal tension between gravitational attraction and cosmic expansion creates the dynamic balance that maintains the web's architecture across deep time, knitting the cosmos into a tapestry of light and shadow that reveals the universe's profound geometric soul. How does the universe build cathedrals from grains of cosmic sand? In the swirling workshops surrounding newborn stars, the scattered ashes of ancient stellar deaths began a dance so gentle it would take millions of years to complete, transforming microscopic particles into entire worlds, through nothing more than patience, gravity, and the tender mathematics of collision, where each tiny impact became a brushstroke in the cosmic masterpiece of planetary creation. Around young stars burning with the fresh fire of nuclear fusion, the enriched inheritance from previous stellar generations settled into magnificent protoplanetary disks, cosmic carousels spinning through space at tremendous speeds, their lanes filled with the precious elements that earlier stars had forged in their nuclear hearts and scattered through their death throes. These disks glowed softly with infrared warmth as starlight heated the countless particles that would become the construction materials for worlds. In the disks of dust around these stellar infants, the most extraordinary construction project in the universe began with encounters so subtle they operated below the threshold of any earthly comparison. Individual grains of cosmic dust, each smaller than particles of cigarette smoke, started their patient aggregation process, binding together through electrostatic forces and molecular attractions that functioned like cosmic glue on the smallest imaginable scales. The construction unfolded with the patience of deep time, as countless microscopic encounters gradually assembled complexity from the simplest beginnings. Dust grains merged into fluffy aggregates, then compressed into denser pebbles no larger than those scattered on earthly shorelines, following physical laws that operate consistently across all scales, but expressing themselves with particular elegance in the pristine environment of cosmic space. These cosmic pebbles continued their gentle ballet across millions of orbits around their parent star, colliding and merging with the persistence of falling snow accumulating into drifts. Pebbles became rocks, rocks became boulders, boulders became small mountains of accumulated matter, each collision adding mass and gravitational influence to the growing collection of stellar debris, learning to become worlds. As these planetesimals reached sizes measured in kilometers rather than meters, their own gravity became strong enough to reshape them according to the fundamental geometry that governs all matter in the universe. Rocks merged into increasingly spherical forms, following the mathematical imperative that pulls matter toward the most efficient three-dimensional arrangement, gradually transforming irregular chunks of debris into the smooth, rounded shapes we recognize as planetary bodies. Gravity stitched these growing worlds into stable orbits around their parent stars with the precision of cosmic clockwork, creating the delicate gravitational balance between inward attraction and outward momentum that would maintain planetary motion across billions of years. Each world found its orbital home through this dance of physics, establishing the rhythmic celestial mechanics that provide stable platforms for complexity to develop. Within these humble collisions that shaped worlds grain by grain, entire landscapes were silently formed through processes that operated below the threshold of drama, yet above the level of cosmic significance. Mountain ranges emerged from the merger of metallic, rich planetesimals, Ocean basins carved themselves through the impact patterns of water-bearing comets, and atmospheric compositions developed through the complex chemistry of captured gases and sublimating ices. The planetary formation process created not isolated worlds, but complete families of celestial architecture, rocky planets in the warm inner zones where stellar heat had driven away volatile compounds, massive gas giants in the cooler outer reaches where water could freeze and substantial atmospheres could accumulate, and diverse populations of moons formed through satellite capture, collision debris, and gravitational sculpting. Through this patient choreography of accretion and orbital dynamics, the universe transformed the scattered ashes of stellar death into the organized matter of planetary systems, creating the diverse worlds that would serve as cosmic laboratories where the next phase of evolution could unfold. From the gentle collision of cosmic dust, entire stages had been constructed for the drama of chemistry, geology, and eventually the emergence of the phenomenon we call life. What happens when a molecule becomes the universe's most precious treasure? In the vast inventory of cosmic chemistry, one simple arrangement of hydrogen and oxygen would prove more valuable than gold, more essential than starlight itself, creating the liquid medium where atoms could dance together in combinations so intricate that they would eventually teach themselves to reproduce, to evolve, and to contemplate their own existence in pools of possibility that transformed barren worlds into cradles of life. As countless worlds settled into their orbital rhythms around parent stars, the cosmic lottery of planetary formation determined which would remain dry stone and which would become something infinitely more precious. On some fortunate worlds, the delicate balance of distance, temperature, and atmospheric composition allowed water to exist in its liquid state, neither frozen into immobile ice, nor boiled away as invisible vapor, but flowing as the universe's most versatile solvent. Water gathered on these blessed worlds, through processes both violent and gentle, arriving as gifts from the outer reaches of planetary systems where comets had formed in the cold darkness beyond the frost line. These icy messengers, bombarding young planets during the chaotic early epochs of solar system formation, delivered not just water, but the complex organic molecules that had formed in the frigid chemistry of interstellar space. On worlds where conditions allowed, liquid seas began to shimmer under alien skies, sometimes beneath the gentle light of yellow stars like our sun, other times illuminated by the red glow of smaller, longer-lived stellar companions, or even warmed by the tidal forces of massive planetary neighbors. Each ocean represented a unique cosmic experiment in the physics and chemistry of possibility. These planetary seas became far more than simple collections of water molecules. They transformed into vast three-dimensional laboratories where dissolved minerals from weathered rocks mixed with organic compounds from space, creating chemical soups of unprecedented complexity. Ocean currents stirred these mixtures across planetary scales, while thermal vents on seafloors added energy and exotic chemistry to the aquatic blend. Where water flowed, the fundamental possibility of life was etched into the fabric of planets through the unique properties that make H2O so essential to complex chemistry. Water's ability to dissolve an enormous variety of substances created the liquid medium where different molecular species could meet, interact, and form the intricate chemical networks that simple gas phase reactions could never achieve. The oceans became nature's first chemistry sets, where carbon compounds from space could combine with phosphorus, sulfur, and trace metals leached from planetary crusts. In these aquatic environments, molecules had the freedom to move, collide, and bond in 3 dimensions, while the liquid medium provided the stability needed for complex molecular structures to persist and evolve over time. Within these vast laboratories, the boundary between chemistry and biology began to blur as self-organizing molecular systems emerged from the chaos of random chemical reactions. Lipid molecules learned to form membrane boundaries, creating the first cellular compartments. RNA molecules discovered their ability to both store information and catalyze chemical reactions, bridging the gap between chemistry and genetics. These oceans became the canvases on which chemistry could paint its most ambitious masterpiece, biology itself. In the patient waters of countless worlds, molecular complexity crossed the threshold from mere chemistry to something entirely new. Systems that could grow, reproduce and evolve, transforming planets from collections of rock and water into living worlds where the universe could begin the long journey toward consciousness. The significance of these liquid seas extended far beyond their planetary boundaries, for they represented the universe's first successful attempt to create environments stable and complex enough to support the emergence of life, proving that under the right conditions, cosmic evolution could transcend physics and chemistry to create the phenomenon of biology. How does the universe conduct its most intimate symphony using only invisible forces? In the delicate gravitational choreography between worlds and their orbital companions, distant moons became cosmic conductors, reaching across empty space to orchestrate the rise and fall of planetary oceans with such precision that they transformed static seas into rhythmic heartbeats, creating the temporal pulse that would nurture life's earliest experiments in adaptation and evolution. On worlds blessed with both liquid oceans and substantial moons, gravity revealed its most subtle and profound artistry through the phenomenon of tides, invisible hands reaching across hundreds of thousands of kilometers to caress planetary waters with forces so gentle they could barely lift a feather, yet so persistent they could reshape entire coastlines across geological timescales. Moons pulled on oceans with the patient insistence of cosmic metronomes, creating gravitational gradients that stretched water toward the lunar source, while simultaneously creating complementary bulges on the opposite side of the planet. These dual tidal bulges traveled around each world as it rotated, generating the eternal rhythms of ebb and flow that transformed shorelines from static boundaries into dynamic interfaces between land and sea. The resulting tidal dances became far more than simple mechanical phenomena. They evolved into planetary-scale life support systems that stirred oceans, mixed nutrients, and created the environmental gradients that would prove essential for biological complexity. As waters rose and fell with metronomic precision, they carved coastal channels, filled tidal pools, and exposed vast intertidal zones to the alternating influences of marine and terrestrial chemistry. These rhythmic cycles shaped coastlines through processes both gentle and relentless, carving rocky shores into intricate patterns of caves, arches, and tidal pools, while simultaneously depositing sediments in vast coastal plains that would become some of the most biologically productive regions on their respective worlds. The gravitational partnership between planets and moons became a cosmic earth-moving operation conducted entirely through the medium of flowing water. Within these ever-changing tidal zones, the first sparks of life may have found the dynamic environments they needed to bootstrap the complex chemistry of biology. Tidal pools became natural laboratories where organic molecules could concentrate during low tide, then mix and disperse during the next tidal cycle, creating the oscillating chemical conditions that favor the formation of self-organizing molecular systems. The regular alternation between wet and dry conditions in tidal zones created selection pressures that encouraged the development of molecular systems capable of surviving environmental changes, a crucial step toward the robust, adaptable chemistry that characterizes living organisms. In these rhythmic environments, molecules learned the art of persistence through variation. Tidal mixing also served as a planetary circulation system, stirring ocean waters to prevent stagnation, while distributing dissolved nutrients, minerals, and organic compounds across vast distances. This gravitational stirring created the chemical gradients and energy flows that complex ecosystems would eventually require, establishing the oceanic equivalent of atmospheric weather systems. The influence of tides extended beyond immediate coastal effects to shape entire planetary climates through their impact on ocean circulation patterns. By driving deep water currents and influencing the distribution of warm and cold water masses, tidal forces help stabilize planetary temperatures and create the long-term environmental stability that complex life requires to evolve and flourish. Gravity's reach was revealed to be not only cosmic in scale, but intimate in effect, guiding even the smallest waves lapping against primordial shores, while simultaneously orchestrating the vast oceanic systems that would make these worlds suitable for life. In the eternal dance between planets and their moons, the universe discovered how to create the rhythmic environments where chemistry could learn to become biology. What sculptor could work for 4 billion years without losing patience, carving masterpieces from the living clay of molecular possibility? In the most extraordinary art project ever undertaken, evolution revealed itself as the universe's most persistent artist, working not with marble or bronze, but with the malleable chemistry of life itself, sculpting countless forms of breathtaking beauty and complexity through nothing more than time, variation, and the gentle selection pressures of environmental change. Life, once sparked in the primordial laboratories of ancient oceans, began its magnificent unfolding with a patience that dwarfs human comprehension. The first simple forms, little more than self-replicating molecules wrapped in protective membranes, carried within their primitive chemistry the unlimited potential for all the biological complexity that would eventually grace their planetary homes. These early pioneers of existence faced a world both hostile and full of opportunity, where survival required the mastery of fundamental challenges that would shape all future evolution. They learned to harvest energy from their surroundings, to reproduce with sufficient accuracy to maintain their essential chemistry, while allowing enough variation to adapt to changing conditions and to compete for limited resources in the crowded molecular ecosystems of early life. Over hundreds of millions of years, simple forms gradually became complex through the accumulation of countless small innovations, each tested against the relentless criteria of survival and reproduction. Single cells learned to cooperate, forming the first multicellular communities where specialized cells could divide the labor of existence, creating organisms capable of growing larger, living longer, and exploring new environments. The quiet patience of evolution worked through mechanisms both random and directional, as genetic mutations provided the raw material of variation, while natural selection served as the cosmic editor, preserving advantageous changes while discarding those that hindered survival. This partnership between chance and necessity created a creative process more inventive than any human imagination, generating solutions to biological challenges that engineers still struggle to understand. As life diversified and spread across available environments, evolution discovered an endless array of architectural solutions to the problems of existence. Some organisms mastered the art of photosynthesis, learning to capture stellar energy directly and transform it into biological chemistry. Others became sophisticated predators, developing sensory systems and locomotion strategies that would inspire future technologies. The evolutionary process sculpted countless creatures, each representing a unique experiment in the possibilities of organized matter and energy. From microscopic bacteria that could thrive in boiling water to complex organisms that developed eyes, wings, and eventually nervous systems capable of processing information about their surroundings, life explored every conceivable niche in the expanding landscape of biological possibility. Each organism became a reflection of cosmic chemistry guided by time's relentless hand, embodying in its structure and behavior the successful solutions that evolution had discovered for the challenges of its particular environment. The carbon forged in stellar hearts, the oxygen released by ancient photosynthesis, and the trace elements scattered by supernovae found new expression in the intricate molecular machinery of living systems. Over billions of years, this patient process transformed barren planets into biospheres of stunning complexity, where countless species engaged in ecological relationships that spanned from microscopic symbioses to planetary-scale biogeochemical cycles. Evolution had become the universe's method for exploring the full potential hidden within the chemistry of life, proving that given enough time, matter and energy could organize themselves into forms capable of growth, adaptation, and even the contemplation of their own cosmic origins. Through evolution's long patience, the universe discovered how to transform simple chemistry into the phenomenon of biology, and eventually into the emergence of consciousness, the cosmos learning to know itself through the evolved complexity of living minds. When did the universe first open its eyes? In the most extraordinary transformation in cosmic history, matter that had journeyed from the nuclear hearts of dying stars through billions of years of planetary chemistry and biological evolution achieved something unprecedented: the ability to contemplate its own existence, to wonder about its origins, and to recognize itself as both observer and participant in the grand cosmic story that began with the first whisper of creation. The path to consciousness began with the evolution of nervous systems, as multicellular organisms discovered the advantages of specialized cells dedicated to processing information about their environment. Simple nerve networks evolved into increasingly sophisticated neural architectures, each advancement allowing organisms to respond more effectively to the complex challenges of survival in dynamic ecosystems. Over hundreds of millions of years, evolution sculpted brains of growing complexity, from the primitive nerve clusters of early animals to the elaborate neural networks that could process sensory information, store memories, and coordinate increasingly sophisticated behaviors. Each evolutionary step built upon previous innovations, gradually assembling the biological machinery that would eventually support the phenomenon of conscious experience. The emergence of consciousness represented more than just another evolutionary adaptation. It marked the moment when the universe developed the capacity for self-reflection. From matter that once blazed in the nuclear furnaces of ancient stars, organized into planetary systems, and complexified through biological evolution, awareness finally emerged as the cosmos discovered how to know itself through the evolved complexity of living minds. On a small blue planet orbiting an ordinary yellow star in an unremarkable spiral galaxy, consciousness awakened with qualities that transcended mere survival. Early awareness began with simple recognition, the ability to distinguish self from environment, to remember past experiences, and to anticipate future events. But consciousness proved to be far more than an advanced survival tool. This cosmic awakening carried within it something revolutionary. Curiosity itself, the drive to understand, rather than simply to survive. Conscious beings began asking questions that had no immediate survival value yet possessed profound significance, wondering about the nature of existence, the structure of reality, and their place in the vast tapestry of cosmic time and space. The fragile yet profound nature of consciousness revealed itself through its remarkable properties: self-awareness, intentionality, and the ability to contemplate abstract concepts that extended far beyond immediate sensory experience. Conscious minds could envision possibilities that did not yet exist, create mental models of reality, and even imagine their own non-existence. Perhaps most remarkably, consciousness developed the capacity to reflect on the very universe that had created it. Through the evolved neural networks of thinking beings, stellar carbon and oxygen atoms acquired the ability to contemplate the cosmic processes that had forged them. The universe had become capable of scientific investigation, artistic expression, and philosophical inquiry, examining its own structure and history through the consciousness it had gradually assembled. This awakening transformed the cosmic story from a purely physical narrative into something deeper, a universe that could appreciate its own beauty, investigate its own laws, and wonder about its own purpose. Through consciousness, the 14 billion-year journey from quantum fluctuations to stars to planets to life achieved its most extraordinary milestone, the emergence of minds capable of understanding and marveling at the very cosmic odyssey that had brought them into existence. In developing consciousness, the universe had created not just observers of its magnificence, but participants capable of extending the creative process through imagination, discovery, and the endless quest to understand the profound mystery of existence itself. When did the universe first see itself reflected in the eyes of conscious beings? In the moment early humans lifted their gaze from earthly concerns to contemplate the star-scattered dome above, a profound transformation occurred. The cosmos that had spent 14 billion years creating conscious observers finally found itself being observed, studied, and woven into the stories that would shape human culture and guide our species across oceans, continents, and eventually into space itself. Looking upward from their terrestrial home, early humans encountered a celestial theatre of breathtaking complexity and beauty. The night sky revealed itself as a vast canvas painted with thousands of points of light, each star a distant sun burning with nuclear fire across unimaginable distances. Yet to human eyes, these cosmic furnaces appeared as gentle pinpricks of illumination, close enough to touch yet distant enough to inspire wonder about worlds beyond immediate experience. The human mind evolved to find patterns in the environment as a survival mechanism, began discovering shapes and relationships among the stellar arrangements overhead. Constellations emerged from random stellar positions as consciousness imposed order on cosmic chaos, seeing bears and hunters, swans and serpents dancing across the celestial sphere, transforming the alien geometry of three-dimensional space into familiar two-dimensional stories. Early stargazers noticed that certain stars wandered against the background of fixed stellar patterns, following mysterious paths that changed with the seasons. These wandering stars, the planets of our solar system, became harbingers of seasonal change and agricultural timing, their movements encoding information about terrestrial cycles that proved essential for survival in agricultural societies developing across the planet. They told stories that bound earthly experience to celestial phenomena, creating mythologies that explained not just the positions and movements of stars, but the fundamental questions of human existence: where we came from, why we are here, and what our relationship might be to the vast cosmic architecture surrounding our small world. These stellar stories became the foundation of human culture, philosophy, and early science. From careful observation of stellar movements, human civilization built the first calendars, precise systems for tracking time that enabled the coordination of agricultural activities, religious ceremonies, and social gatherings across entire communities. The stars became humanity's first clock, their predictable motions providing the temporal framework that complex societies required to function effectively. Maritime civilizations discovered that stellar patterns could serve as cosmic navigation systems, with certain stars reliably indicating direction across vast oceanic expanses. The night sky transformed into a celestial map that enabled human exploration and trade across previously insurmountable distances, literally guiding our species from isolated communities to global civilization. The night sky became a mirror of human imagination, reflecting back not just the light of distant suns, but the dreams, fears, and aspirations of conscious beings contemplating their place in the cosmic order. In studying the heavens, humans were unconsciously beginning the scientific investigation of their own cosmic origins, tracing the very stellar processes that had forged the elements composing their bodies and minds. This celestial engagement marked the beginning of astronomy, mathematics, and systematic observation of natural phenomena. By watching the sky, humans developed the intellectual tools that would eventually enable them to understand stellar evolution, planetary formation, and cosmic history, revealing that we are not separate from the universe we observe, but integral participants in the cosmic story that created us. The sky had become more than a source of light and wonder. It had become humanity's first teacher, guide, and inspiration for the scientific quest that would eventually reveal our deep connection to the cosmic processes that began with the birth of time itself. What if the universe had been writing its autobiography in symbols that took humanity millennia to decode? In the most profound translation project ever undertaken, curious minds discovered that beneath the chaos of natural phenomena lay a hidden language of mathematical precision, elegant equations that revealed the cosmos as a vast symphony where every note, from quantum vibrations to galactic rotations, follows the same fundamental harmonies that began playing at the moment of creation. The journey from storytelling to scientific understanding began when ancient minds noticed that celestial events followed predictable cycles rather than the whims of divine personalities. Solar eclipses returned with mathematical regularity, planetary positions could be calculated in advance, and tidal patterns obeyed numerical relationships that enabled accurate prediction of coastal flooding and safe harbor times. With time and patient observation, myths gave way to science, as humanity learned to distinguish between the comforting stories we create about nature and the actual mechanisms through which natural processes operate. This intellectual revolution required abandoning anthropomorphic explanations in favor of mathematical descriptions that, while less emotionally satisfying, proved infinitely more powerful for understanding and predicting natural phenomena. Gradually, careful observers recognized that patterns in natural phenomena could be captured in mathematical relationships of startling precision and universal applicability. Galileo's inclined plane experiments revealed that falling objects accelerated according to mathematical formulas, while Kepler's planetary observations showed that orbital motions followed geometric laws that could be expressed through elegant equations describing elliptical paths through space. The true breakthrough occurred when Newton demonstrated that patterns became mathematics through the recognition of underlying forces operating according to universal principles. His gravitational equations unified earthly and celestial mechanics, showing that the mathematical relationship governing an apple's fall to Earth was identical to the force maintaining the Moon's orbit around our planet and planets' journeys around the Sun. Mathematics became the language of the universe when scientists realized that natural laws could be expressed through equations that remained constant across all scales of space and time. Maxwell's electromagnetic mathematics demonstrated that light, radio waves, and X-rays were all variations of the same fundamental phenomenon, while Einstein's field equations revealed that gravity itself arose from the curvature of space-time according to mathematical relationships of breathtaking elegance. Through these equations, the hidden rhythms of nature were revealed with clarity that connected the smallest quantum fluctuations to the largest cosmic structures. The mathematical constants, appearing in atomic physics, also governed stellar evolution, while the geometric principles describing molecular shapes also determined the spiral architecture of galaxies spinning through space. The most profound discovery was that the same fundamental forces shaping galaxies billions of light years away also guided falling apples in earthly orchards, ocean tides lapping against coastal shores, and electrons orbiting atomic nuclei. Universal mathematical relationships appeared everywhere, suggesting that beneath the apparent diversity of natural phenomena lies a deep mathematical unity connecting all cosmic processes. This mathematical unity implied something profound about the nature of reality, that beneath the apparent diversity of natural phenomena lies a deep mathematical order that connects the smallest quantum events to the largest cosmic structures. The universe had revealed itself to be not just mathematically describable, but fundamentally mathematical in its essential nature. Through learning the language of mathematics, humanity gained the ability to participate consciously in cosmic processes that had been operating unconsciously for billions of years. We could now predict eclipses, calculate orbital trajectories, and understand our place within the vast mathematical symphony that the universe had been composing since its first quantum fluctuation whispered the initial equations of existence into being. What happens when humanity learns to see beyond the prison of unassisted vision? In one of the most transformative moments in intellectual history, the invention of the telescope shattered humanity's cosmic perspective like glass breaking to reveal infinite space beyond, suddenly showing that our familiar Earth was not the center of creation, but merely one small world drifting through an immensity that challenged every assumption about our place in the grand architecture of existence. The first telescopes were simple arrangements of lenses that gathered more light than human eyes could collect alone, but their impact on human understanding proved revolutionary beyond imagination. When Galileo first pointed his crude optical instrument toward the heavens in 1609, he transformed dots of light into worlds, revealing that the moon possessed mountains and craters, like a celestial landscape, that Jupiter hosted its own family of orbiting satellites, and that Venus showed phases, like a small moon. These telescopic revelations opened windows to the cosmos that had remained forever sealed to naked eye observation. The Milky Way, appearing as a faint band of light across earthly skies, resolved into countless individual stars when viewed through telescopic magnification. What had seemed like scattered cosmic dust revealed itself as stellar cities so numerous that they challenged human comprehension and suggested a universe far vaster than previous generations had imagined. As telescopic technology improved across centuries of refinement, moons, planets, nebulae, and galaxies appeared with increasing clarity and detail. Saturn displayed its magnificent ring system like a cosmic jewel suspended in space, while Mars showed seasonal changes that hinted at weather patterns on an alien world. The outer planets emerged from cosmic darkness as telescopes revealed Uranus and Neptune orbiting in the cold reaches beyond Saturn. Nebulae, previously dismissed as cosmic clouds of little significance, transformed under telescopic scrutiny into vast stellar nurseries where new stars were being born from gravitational collapse of interstellar gas and dust. Some nebulae revealed themselves as entire galaxies, island universes containing billions of stars, each potentially hosting planetary systems of their own, scattered across distances so immense that light from the nearest external galaxies had been traveling for millions of years to reach Earth. Through increasingly powerful telescopic observations, the revelation became undeniable. Earth was not the center of the universe, but one world among countless others, orbiting an ordinary star in the outer reaches of an unremarkable spiral galaxy that was itself one of billions of similar galactic structures distributed throughout observable space. Humanity's cosmic address expanded from a singular central position to coordinates in a vast galactic suburb. This telescopic revolution showed that knowledge expanded exponentially when human vision was augmented by technology, revealing layers of cosmic architecture that remained invisible to unassisted observation. Each improvement in telescopic capability uncovered new scales of cosmic structure, from planetary systems to stellar clusters to galactic superclusters, demonstrating that the universe operated on scales that dwarfed human experience. With expanded knowledge came a fundamental transformation in human perspective, a growing humility before the immensity of creation that replaced anthropocentric arrogance with wonder at our cosmic insignificance and cosmic connection. The telescope had become humanity's first tool for cosmic exploration, launching the scientific quest that would eventually reveal our deep kinship with stellar processes and galactic evolution. Through telescopic eyes, humanity began to see itself not as the purpose of creation, but as its product, conscious observers arising from cosmic processes that had been operating for billions of years before Earth formed, creating the elements, stars, and planets necessary for life through mechanisms far grander and more beautiful than any mythological account of our origins. What if the universe has been painting masterpieces in colors that human eyes were never designed to see? In the most profound expansion of cosmic vision since the invention of the telescope, 20th century astronomers discovered that visible light represents only a tiny fraction of the electromagnetic symphony that fills space, revealing that beneath the familiar cosmos of optical astronomy lay hidden universes of radio waves, X-rays, and infrared radiation that told stories of cosmic violence, stellar birth, and gravitational phenomena so extreme they challenged the boundaries of physical understanding. For centuries, astronomy had been limited to the narrow window of visible light that human evolution had equipped us to detect, wavelengths spanning from red to violet that represent less than 1% of the electromagnetic spectrum radiating throughout the universe. This cosmic myopia meant that most of the universe's electromagnetic activity remained as invisible to optical telescopes as radio broadcasts are to human hearing. The breakthrough came when engineers learned to build instruments capable of detecting electromagnetic radiation beyond the visible spectrum, opening entirely new channels of cosmic communication. Radio telescopes revealed that space was filled with electromagnetic chatter from sources that appeared completely silent in visible light, pulsars broadcasting precise timing signals, galaxies emitting powerful radio beams, and the cosmic microwave background itself, whispering the fossilized echo of creation's first light. Beyond visible light, these new instruments revealed hidden universes of spectacular activity and beauty. Radio astronomy uncovered vast clouds of interstellar hydrogen, mapping the spiral structure of galaxies, while showing that some galaxies possessed enormous lobes of radio emission extending far beyond their visible boundaries, powered by supermassive black holes lurking at their centers. X-ray telescopes, operating from space above Earth's protective atmosphere, unveiled the most violent processes in the cosmic theater. They showed galaxies forming through gravitational collisions that heated intergalactic gas to millions of degrees, neutron stars spinning hundreds of times per second while beaming high-energy radiation across space, and stellar mass black holes feeding on material torn from companion stars in gravitational dances of mutual destruction. Infrared observations penetrated cosmic dust clouds that blocked visible light, revealing stars dying in spectacular planetary nebulae, while simultaneously showing new stars being born in the heart of stellar nurseries. The infrared universe glowed with the heat signatures of cosmic processes, brown dwarfs too small to sustain nuclear fusion, distant galaxies whose light had been redshifted by cosmic expansion, and the warm dust lanes threading through spiral galaxies like cosmic circulatory systems. Each wavelength regime told different stories about the same cosmic phenomena, like viewing a symphony through multiple senses simultaneously. A galaxy that appeared as a peaceful spiral in visible light might reveal itself as a powerful radio source in long wavelengths, an X-ray emitter at its center where a supermassive black hole was feeding, and a complex network of star-forming regions glowing in infrared radiation. These multi-wavelength observations revealed that black holes, previously theoretical curiosities, were among the universe's most important cosmic engines, feeding on surrounding matter while powering jets of particles that extended for millions of light years, regulating star formation in their host galaxies, and creating some of the most energetic phenomena observable anywhere in the cosmos. The cosmos proved richer and stranger than human eyes alone could ever know, filled with invisible architectures of electromagnetic radiation that painted a far more dynamic and interconnected universe than optical astronomy had ever suggested. Through learning to see in wavelengths beyond visible light, humanity had gained cosmic X-ray vision, revealing the universe as a place of constant electromagnetic conversation between objects separated by millions of light years, yet connected through the invisible threads of radiation that carry information across the cosmic web. What if most of the universe is written in invisible ink? In one of the most humbling discoveries in scientific history, astronomers realized that everything we can see, every star, planet, galaxy, and nebula glowing across the cosmic tapestry, represents only a small fraction of the matter that actually exists, while the vast majority of cosmic mass remains completely invisible, detectable only through its gravitational influence on the luminous matter that forms the visible architecture of space. The mystery began when astronomers carefully measured how quickly galaxies rotate, expecting to find that outer stars orbit more slowly than inner ones, just as outer planets in our solar system orbit the sun more leisurely than inner worlds. Instead, they discovered something impossible according to classical physics. Galaxies spun too quickly for visible matter alone to hold them together through gravitational attraction. According to Newton's laws of motion and gravity, the outer regions of spiral galaxies should have been flung into space long ago by centrifugal forces, their stars scattered across intergalactic space like sparks thrown from a spinning wheel. Yet these galactic structures persisted with perfect stability, rotating as rigid bodies rather than the loose collections of gravitationally bound stars that visible matter alone could support. The only possible explanation required accepting that an unseen presence pervaded space, invisible matter, that generated sufficient gravitational attraction to bind galactic structures together despite their rapid rotation. This dark matter, as astronomers named it, had to outweigh all visible matter by more than 5-to-1, meaning that stars, planets, gas clouds, and every luminous object we observe represents less than 20% of the universe's total mass. Though completely invisible to electromagnetic radiation across all wavelengths, dark matter revealed its presence through gravitational effects that could be measured with exquisite precision. Galaxy clusters showed clear evidence of dark matter through gravitational lensing, the bending of light from distant galaxies, by the immense but invisible mass concentrations that pervaded these cosmic metropolitan areas. Computer simulations of cosmic structure formation demonstrated that dark matter provided the gravitational scaffolding upon which ordinary matter could collect to form the first stars and galaxies. Without dark matter's invisible architecture, the universe would have remained a nearly uniform soup of hydrogen and helium, lacking the density fluctuations necessary to collapse into stellar nurseries and galactic cities. This mysterious substance shaped the very structure of the universe through its gravitational influence, creating the cosmic web of filaments and voids that determined where galaxies would form and how they would cluster across cosmic space. Dark matter halos became the invisible foundations upon which visible galaxies were constructed. Like cosmic urban planning, conducted by an architect who worked entirely through gravitational engineering. The nature of dark matter particles remained one of the deepest mysteries in physics. They interact gravitationally, but appear immune to electromagnetic forces, passing through ordinary matter without friction or collision. Billions of dark matter particles stream through Earth every second, passing through rock, water, and human bodies without leaving any trace of their passage except their collective gravitational influence on cosmic structure. Despite being invisible, dark matter emerged as the universe's primary construction material, the gravitational glue that held cosmic architecture together and enabled the formation of the galactic environments necessary for stellar evolution, planetary formation, and ultimately the emergence of complexity and consciousness. The cosmos revealed itself to be far stranger than human intuition suggested, a universe where the invisible majority silently shapes the destiny of everything we can observe, proving that reality extends far beyond the boundaries of human perception into realms that challenge our most fundamental assumptions about the nature of matter and space. What if empty space itself possesses a hidden power that grows stronger as the universe expands? In the most counterintuitive discovery in cosmic history, astronomers found that the universe's expansion, which gravity should be slowing down like a ball thrown upward eventually succumbing to Earth's pull, is instead accelerating, driven by a mysterious force that appears to emerge from the vacuum of space itself, pushing galaxies apart with ever-increasing strength in defiance of everything we thought we understood about cosmic evolution. For decades after Hubble discovered that the universe was expanding, astronomers assumed that this expansion must be gradually slowing down under the gravitational influence of all the matter distributed throughout space. Just as a rocket escaping Earth's gravity eventually slows its ascent, cosmic expansion should decelerate as gravity exerts its attractive influence across billions of light-years of space filled with stars, galaxies, and dark matter. The expectation seemed so reasonable that the primary question was whether the universe contained enough matter to eventually halt expansion entirely, causing a cosmic collapse back toward a big crunch, or whether expansion would continue forever, but at an ever-decreasing rate. Both scenarios assumed that gravity was winning the cosmic tug-of-war against the momentum of expansion inherited from the Big Bang. But when astronomers used distant supernovae as cosmic lighthouses to measure how expansion had changed over billions of years, they discovered something that shattered every theoretical prediction. Not only was the universe expanding, it was accelerating, growing faster and faster as time progressed, as if some invisible force was actively pushing galaxies apart with strength that increased rather than decreased with cosmic age. This observation required the existence of an unknown energy that operated in opposition to gravity's attractive influence, a repulsive force that became more dominant as the universe aged, and matter became more diluted through expansion. Unlike all known forms of matter and energy, this dark energy exhibited the bizarre property of growing stronger as space itself expanded, maintaining constant density even as cosmic volume increased exponentially. The implications were staggering. This dark energy comprises roughly 70% of the universe's total energy content, making it the dominant component of cosmic evolution, despite being completely invisible and detectable only through its effect on cosmic expansion. Combined with dark matter's 25% contribution, ordinary matter, everything we can observe directly, represents less than 5% of the universe's total mass and energy. Dark energy operates as a fundamental property of space itself, woven into the very fabric of the cosmic arena, rather than existing as particles or fields that travel through space. As the universe expands and creates more space, it simultaneously creates more dark energy, establishing a positive feedback loop that drives ever faster expansion across cosmic time. This acceleration means that distant galaxies are racing away from us at increasing speeds, and that most of the observable universe is already moving away faster than light, not because anything is violating the speed limit of relativity, but because space itself is expanding so rapidly that distant regions disappear beyond our cosmic horizon, becoming forever unobservable from our local position in space-time. The discovery of dark energy transformed our understanding of cosmic destiny from scenarios dominated by matter and gravity to a future shaped by accelerating expansion. Rather than eventual collapse or gradual cooling, the universe appears destined for eternal acceleration, with galaxies becoming increasingly isolated as space stretches between them at ever-growing rates. This dark energy remains one of the greatest mysteries in physics, a force that defies easy explanation yet dominates the universe's evolution, challenging our most fundamental theories about the nature of space, time, and energy, while reshaping our vision of cosmic fate, from gravitational collapse to infinite expansion, driven by the hidden power embedded in empty space itself. What happens when gravity becomes so powerful that it breaks the universe's most fundamental rule, that nothing can travel faster than light? In the cosmic laboratories, where matter collapses beyond all reasonable limits, space and time themselves surrender to gravitational forces so extreme that they create regions where the normal laws of physics dissolve into mathematical singularities, forming cosmic paradoxes that serve as both the universe's most efficient destroyers and its most influential architects. Black holes emerge when gravity pushes matter to its ultimate extremes, compressing the cores of massive stars beyond the point where any known force can resist further collapse. As stellar matter falls inward under its own gravitational attraction, it reaches a critical threshold where the escape velocity, the speed needed to break free from gravitational pull, exceeds the speed of light itself, creating a boundary in space-time beyond which nothing, not even electromagnetic radiation, can return to the outside universe. This event horizon marks the point of no return, where the curvature of space-time becomes so extreme that all paths lead inward toward the central mass, regardless of the direction or speed of motion. Light itself becomes trapped in these gravitational wells, unable to climb out of the curved space-time geometry that Einstein's equations predict forms around any sufficiently compact mass concentration. At their centers, space-time folds into singularities, mathematical points where density becomes infinite, and the familiar concepts of space and time lose their meaning. These singularities represent the breakdown of our current physical theories, suggesting that black holes conceal realms where quantum mechanics and general relativity must somehow merge into a unified description of reality that physicists have yet to discover. Yet despite their reputation as cosmic vacuum cleaners, black holes reveal themselves as paradoxes of physics, simultaneously serving as both destroyers and creators in the cosmic ecosystem. While they consume matter that ventures too close to their event horizons, they also regulate the formation and evolution of galaxies through their gravitational influence and the enormous energies they release when feeding on surrounding material. Supermassive black holes containing millions or billions of times the mass of our Sun reside at the centers of most galaxies, where they serve as gravitational anchors that help organize stellar orbits across vast distances. When matter spirals into these cosmic giants, it forms accretion disks that heat to billions of degrees, radiating more energy than entire stellar populations, and creating some of the most luminous objects observable in the universe. These feeding events can trigger powerful jets of particles that extend for millions of light-years beyond their host galaxies, regulating star formation across galactic scales and influencing the distribution of matter throughout cosmic space. Black holes thus sculpt galactic architecture through processes that connect the smallest scales of particle physics to the largest structures in the observable universe. Perhaps most intriguingly, black holes may hide keys to deeper laws of reality within their enigmatic interiors. The information paradox, the question of what happens to information that falls past an event horizon, challenges our understanding of quantum mechanics and thermodynamics, suggesting that black holes possess properties that transcend classical physics and point toward new principles governing the relationship between matter, energy, space, and time. Hawking radiation, predicted to emerge from quantum fluctuations near event horizons, implies that black holes slowly evaporate over cosmic timescales, returning their mass energy to the universe while raising profound questions about the conservation of information and the ultimate fate of matter that has crossed the threshold from which classical physics says nothing can return. Through their extreme properties, black holes serve as natural laboratories for testing the boundaries of physical law, revealing that the universe contains regions where reality operates according to principles that stretch our theoretical understanding to its limits while shaping cosmic evolution through mechanisms that span from quantum to galactic scales. What if the universe has been composing music for billions of years, playing instruments so massive they bend the fabric of space itself? In the most profound auditory discovery of our time, scientists learned that violent cosmic events create ripples in space-time that travel across the universe at light speed, carrying the acoustic signatures of gravitational catastrophes that occurred millions of years ago, transforming Earth into a cosmic listening post where we can finally hear the universe's deep bass notes played on scales that dwarf human imagination. For over a century after Einstein predicted their existence, gravitational waves remained theoretical curiosities, mathematical consequences of general relativity that seemed forever beyond experimental detection. These ripples in space-time itself were expected to be so subtle that even the most violent cosmic events would produce distortions smaller than 1/10,000th the width of a proton, requiring measurement precision that pushed engineering to its absolute limits. The breakthrough came when scientists learned to detect these infinitesimal stretches and compressions of space using laser interferometry, shooting coherent light beams down precisely measured corridors several kilometers long and monitoring tiny changes in the time it takes light to travel these distances. When gravitational waves pass through Earth, they alternately stretch and squeeze space itself, causing these carefully calibrated measurements to fluctuate in patterns that reveal the cosmic events that generated them. When the first gravitational wave detection was announced in 2015, humanity gained an entirely new sense for perceiving the universe, the ability to feel rather than see cosmic events through their effect on local space-time. The detected signal carried the acoustic signature of two black holes, each roughly 30 times more massive than our Sun, spiraling into each other across millions of years before merging in a final violent embrace that released more energy and gravitational waves than all the stars in the observable universe were producing in electromagnetic radiation at that moment. These ripples in space-time spread from violent cosmic events with unprecedented information content. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass through planets, stars, and entire galaxies without attenuation, carrying pristine information about the cosmic cataclysms that generated them across billions of light-years of space. The detection of merging neutron stars provided even richer cosmic music, as these incredibly dense objects, stellar cores compressed to the density of atomic nuclei, produced gravitational chirps that could be correlated with electromagnetic observations of the same events. These multi-messenger observations revealed gravitational wave astronomy as a new window into cosmic processes that remain invisible to traditional electromagnetic telescopes. Each gravitational wave detection carries the echoes of distant cataclysms encoded in the frequency and amplitude modulations of space-time distortions. The final moments of black hole mergers produce characteristic chirps as orbital frequency increases toward coalescence, while neutron-star collisions generate more complex waveforms that reveal information about the exotic physics of matter compressed beyond nuclear density. As detector sensitivity improves and new gravitational wave observatories come online around the world, the universe reveals itself as a vast concert hall where cosmic events produce a symphony of space-time music spanning frequencies from fractions of a hertz to thousands of cycles per second. Binary black holes provide deep bass notes, neutron-star mergers contribute higher frequency melodies, and the cosmic background of gravitational waves from the early universe may eventually be detected as the fundamental drone, underlying all cosmic music. Through gravitational wave astronomy, the universe itself can finally be heard as a cosmic symphony, transforming our relationship with the cosmos from passive observation to active listening, where Earth becomes a sensitive microphone detecting the gravitational music that massive objects have been playing throughout cosmic history, a celestial concert that began with the universe's first moments and continues with every violent event that shapes the evolution of space and time. What if every star carries within its nuclear heart the script of its own destiny, written in the fundamental physics that will determine whether it dies gently or spectacularly. In the vast stellar theatre of the galaxy, each burning sun follows a predetermined path toward one of several possible endings, some fading gracefully into cosmic retirement, others collapsing into the densest matter in the universe, and the most massive exploding with such violence that they outshine entire galaxies while seeding space with the elements needed for future generations of worlds and life. Throughout their nuclear-burning lifetimes, stars engage in a constant battle between the inward crush of their own gravity and the outward pressure generated by fusion reactions in their cores. This delicate balance determines not only how long each star will shine, but also the dramatic nature of its ultimate demise. The mass with which a star is born becomes its cosmic destiny, determining which of several possible endings awaits at the conclusion of its thermonuclear career. Stars like our Sun, with modest masses that burn their hydrogen fuel slowly and steadily, are destined for gentle deaths that unfold over billions of years. As their core hydrogen exhausts, they expand into red giants, growing so large that their outer layers barely remain gravitationally bound to their distant cores. These aging stars eventually shed their outer atmospheres in beautiful planetary nebulae, leaving behind their collapsed cores as white dwarf stars, objects the size of Earth but containing the mass of the Sun, glowing with residual heat that will take trillions of years to radiate away. More massive stars face increasingly dramatic fates as their greater gravitational attraction compresses their cores to higher temperatures and densities. These stellar giants burn through successive layers of nuclear fuel, hydrogen, helium, carbon, and silicon, in an accelerating cascade of fusion reactions that builds heavier elements in their cores while simultaneously sealing their doom by creating iron, the nuclear ash that cannot be burned for energy. When massive stars attempt to fuse iron, they encounter the fundamental limit where nuclear reactions consume rather than produce energy. Their cores collapse in less than a second, compressing matter to densities that crush protons and electrons together into neutrons, creating objects so dense that a teaspoon would weigh as much as a mountain. These neutron stars represent matter in its most concentrated form outside of black holes, atomic nuclei scaled up to stellar proportions. The most massive stars die in supernovae that release more energy in a few seconds than our Sun will produce over its entire 10 billion-year lifetime. These stellar explosions are visible across cosmic distances, briefly outshining entire galaxies as shock waves tear through the star's outer layers at thousands of kilometers per second, heating gas to billions of degrees and creating the extreme conditions necessary to forge elements heavier than iron through rapid neutron capture. Each stellar death writes a chapter in the ongoing story of cosmic creation by scattering the elements forged in stellar cores throughout surrounding space. The calcium in future bones, the iron in blood, the oxygen in every breath, all were created in stellar furnaces and distributed by stellar deaths. Supernovae also trigger the collapse of nearby gas clouds, initiating new cycles of star formation that continue the cosmic recycling program that transforms stellar ashes into new generations of stars, planets, and eventually life. Through their varied fates, stars reveal themselves as both temporary and eternal, individual stellar lives ending after millions or billions of years, while their elemental legacy persists indefinitely in the cosmic inventory of matter available for future stellar and planetary formation. Death becomes transformation, destruction becomes creation, and every stellar ending enables countless new beginnings in the endless renewal of cosmic evolution. What if the universe's greatest masterpiece is not its brilliant present, but the vast, contemplative silence toward which it slowly journeys? In a cosmic story that spans not mere billions, but trillions of years, the universe reveals its ultimate destiny as a gradual transformation from the vibrant stellar neighborhoods of today into an increasingly sparse and darkening realm where galaxies become isolated islands in an ever-expanding ocean of space, following trajectories written by the same fundamental laws that ignited the first stars and will eventually extinguish the last. The cosmic expansion that began with the universe's birth continues its relentless work, carrying galaxies away from each other at accelerating rates driven by the mysterious dark energy woven into spacetime's fabric. Over the next 100 billion years, this expansion will carry distant galaxies beyond our cosmic horizon, making them forever invisible to future observers as their light becomes too redshifted to detect and their recession speeds exceed the velocity of light through pure spatial expansion. Our own local group of galaxies, the Milky Way, Andromeda, and their smaller companions, will resist this cosmic diaspora for several billion years before their mutual gravitational attraction overcomes the expansion of local space. These galactic neighbors will eventually merge into a single massive elliptical galaxy, temporarily creating one of the largest stellar cities in the increasingly empty cosmic landscape surrounding us. Yet even within these merged galactic structures, the inexorable passage of time will gradually dim the brilliant stellar populations that currently paint the night sky with their nuclear fire. Stars burn through their fuel at rates determined by their mass and nuclear physics, with the most massive consuming their hydrogen in mere millions of years, while smaller red dwarfs will continue shining for trillions of years beyond our sun's eventual demise. As stellar formation slows due to the gradual consumption of interstellar gas and the dispersal of star-forming materials through supernova explosions and stellar winds, the night sky will grow progressively emptier over cosmic timescales that dwarf the entire history of life on Earth. The universe will transition from its current stellar age into the era of dying stars, where brown dwarfs, white dwarfs, and neutron stars become the dominant sources of gradually fading light. Eventually, the universe may enter what cosmologists call the black hole era, when these collapsed stellar remnants become the primary gravitational structures in a cosmos grown cold and dark. Even black holes, however, are not eternal. Hawking radiation ensures that they will slowly evaporate over timescales so vast they make the current age of the universe seem momentary, returning their mass energy to space as elementary particles and photons. The ultimate fate of cosmic expansion depends on the precise nature of dark energy and the fundamental constants that govern spacetime's behavior. If expansion continues accelerating indefinitely, the universe approaches heat death, a state of maximum entropy where energy becomes uniformly distributed and no organized structures can persist. Alternatively, if dark energy proves variable, scenarios ranging from cyclical expansion and contraction to sudden cosmic phase transitions remain possible. Whether ending in cold silence as expansion carries matter beyond interaction range, or in some more dramatic cosmic transformation, the universe's future is vast beyond human comprehension, yet remains entirely determined by the physical laws and constants established in the first moments after creation. The same quantum fluctuations that seeded galaxy formation also encoded the cosmos's ultimate destiny, ensuring that the universe's end will be as lawful and inevitable as its spectacular beginning. In this cosmic perspective, the current era of stellar brilliance and galactic communities represents a brief but magnificent flowering in the universe's long journey from primordial simplicity toward whatever final state awaits in the incomprehensibly distant future. A cosmic story where every chapter, including the last, unfolds according to the mathematical poetry written into reality's deepest structure. How does existence learn to exist when there is no teacher, no stage, no audience, not even the concept of learning itself? At the heart of all wonder lies the most profound question consciousness has ever posed. How did everything we observe, measure, and experience arise from a state so complete in its nothingness that even nothingness would be too much of something? This mystery touches the deepest foundations of reality, where physics meets philosophy in the eternal quest to understand why there is something rather than nothing at all. The question haunts every scientific theory and philosophical framework we construct to understand our cosmic origins. Even our most sophisticated models of the Big Bang begin with initial conditions, quantum fields, space-time geometry, fundamental constants that already assume the existence of mathematical structures and physical laws. But what gave birth to these laws themselves? What breathed existence into the equations that govern reality's unfolding? Scientists have proposed elegant theoretical frameworks to address this ultimate mystery. Quantum field theory suggests that what we call nothing may actually be a seething quantum vacuum filled with virtual particles and energy fluctuations that constantly borrow from and repay the cosmic bank of possibility. Perhaps our universe emerged as a particularly successful quantum fluctuation that managed to become self-sustaining through the strange logic of cosmic inflation. The multiverse hypothesis offers another perspective, suggesting that our cosmos may be one bubble in an infinite foam of universes, each with its own physical laws and constants. In this scenario, the question transforms from why does anything exist to why do we observe the particular combination of physical parameters that allows complexity, stars, and consciousness to emerge. The answer may be anthropic. We observe this specific universe precisely because it is the kind that can produce observers. Cyclical cosmology proposes that the universe undergoes endless cycles of expansion and contraction, big bangs followed by big crunches, in an eternal rhythm where each cosmic death becomes the seed of the next cosmic birth. In this framework, the question of ultimate origins dissolves into infinite regression, where every beginning was preceded by an ending, and every ending enables a new beginning. Yet despite our most sophisticated theories and mathematical models, the mystery remains fundamentally unsolved. The deepest truth may be that the question itself reveals something profound about the nature of reality, that existence is not a problem to be solved, but a gift to be experienced, explored, and celebrated through the consciousness that the universe evolved to contemplate its own origins. Within this ancient mystery lies a truth more beautiful than any answer we might discover. Out of quantum silence came the symphony of stellar fusion. Out of primordial darkness came the light that illuminates every sunrise, and out of apparent nothingness came everything, galaxies spinning through space, planets orbiting stars, and minds capable of wondering about their cosmic heritage while dreaming of futures yet to unfold. The story that began as a whisper before time continues not only in distant galaxies, forming and dissolving across cosmic scales, but in every carbon atom that was forged in stellar cores, every DNA molecule that carries the pattern of life, every neural connection that fires in conscious brains, and every dream that imagines new possibilities for the universe's ongoing creative expression. Perhaps the deepest answer to how everything began from nothing is simply that the universe continues beginning with every moment of awareness, every act of creation, every question asked and wonder felt, ensuring that the cosmic story remains forever unfinished, forever writing itself through the consciousness it created to be both its author and its most appreciative reader.